long as they know.
The kids are like freaking out. They're like, is it next year? And then teacher's like, no, I'm pretty sure she just made it.
Okay, I will go through the essential details that you need to know, which is basically almost everything, but I'll explain it all again. Now, what I have to do is to continue what I was talking about last time. I was talking about phenols. I guess we have to use the more power till you become quieter. I was talking about phenols, and I told you how to name some phenols. And what I need to tell you now is that phenols are acidic. In other words, if you compare the acidity of a phenol with an alcohol, you will find that the phenol is very much more acidic. The pKa of an alcohol is about 18, and the pKa of phenol, this one happens to be 9.89, and you know that the lower the pKa value, the more acidic the compound is. So the question is, why is a phenol acidic? One of the reasons is that if you remove the hydrogen, the acidic hydrogen, so let me take a generic base. If you remove the acidic hydrogen, what you get is a negative charge on oxygen, which you can delocalize into the ring. So you can write that resonance structure. You can write another resonance structure. And finally, you can write yet a third resonance structure. Oops. This is a rubbish. Let me draw it properly. So you get a resonance-stabilized species, whereas if you take cyclohexanol, you can't delocalize that negative charge on the oxygen anyway. It's just got to sit there. So if you can delocalize it, it means that it's more stable than it would otherwise be, and it means, of course, that it's easier to form. So the O- from a phenol is a lot easier to form than the O- from cyclohexanol. So that's why phenols are acidic. Now, how acidic are they? Well, if you take some aqueous sodium bicarbonate, you can extract the phenol into aqueous sodium bicarbonate. You know that you can extract a carboxylic acid, let's say acetic acid. If you shake that with aqueous sodium bicarbonate, you will get sodium acetate, the salt, dissolving in the aqueous layer. And you know from, I suppose you know from undergraduate laboratory work, that if you've got an acid and something that isn't an acid, you can separate them by shaking the mixture with aqueous sodium bicarbonate. And the acid will form a salt and go into the aqueous layer, and the other substance that isn't an acid will stay in the ether layer. You can separate them. And then when you want to recover the acid, you put it in a flask or a separatoric funnel, and you acidify the basic solution, and eventually you get the acid. And of course many students have come to grief in doing that, because they pour the acid into the carbonate, the whole thing froths up and comes out of the flask, or blows the stopper out of the separatory funnel, and then they go crying to the TA, "Oh, what should I do? I lost all my acid." You've got to be very careful. At any rate, these things, like acids, dissolve in aqueous sodium bicarbonate, whereas ordinary alcohols at least apart from those of low molecular weight, which are soluble in water. You know, ethanol is soluble in water. You know, stuff you buy in a liquor store is aqueous ethanol. So those are soluble. Now, what are the reactions of phenols? Well, if you look at the structure of the phenol, let me just circle it, and you ask yourself, what are the reactions of it likely to be? Clearly, there are going to be at least two types of reactions. One type will be reactions of the OH group. The other type will be reactions of the benzene ring. And so let's see what those reactions are. We'll deal first of all with reactions of the OH group. And it would be very reasonable to expect that reactions of the OH group of a phenol would be somewhat similar to reactions of an OH group of an alcohol. And you already know a few reactions of OH groups of alcohols. Has everybody read this? Had enough time to write it down? Okay, let's have a look at reactions of the OH group of alcohols, of phenols rather.
I thought you meant class, and I'm like, God, you're not in class. Yes, I have. I hate it when that happens, because you have to get on the ground. I went so hard that time.
If you treat a phenol with acetic anhydride and some base, or with acetyl chloride and a base, and a common base that would be certainly very suitable would be pyridine, you will get the O-acetate. I'm not going to go through the mechanism, but obviously the base can do one of two things. Either it can remove the proton to give you O- that then attacks the carbonyl in both cases, or the oxygen could attack the carbonyl carbon, and then the base would eventually remove the proton. But the point is that you put an acyl group on the oxygen. And if instead of acetyl chloride, you use this chloride, in other words, a generic one, where R is methyl, ethyl, propyl, cyclohexyl, anything you like, or phenyl, you put an acyl group on the phenolic oxygen. Now, another reaction of alcohols that you know of, and it applies equally to phenols, is if you treat a phenol with a base and you get the phenolate anion, phenolate, and then treat that with an alkyl halide, let's say ethyl iodide. What you will form is an ether. Then you remember that a few weeks ago I told you about the Williamson ether synthesis. And making an ether was the first organic experiment that I ever did when I was a schoolboy. In the class of a Japanese organic chemistry teacher. Now, once you've formed an ether, one of the things you might ask yourself is, if you've got an ether, can you get back the phenol? And the answer is yes, you can. Because if you treat the ether with HBr, what you will get is the phenol plus the bromide corresponding to the other part of the ether. And I'd better tell you how that works, at least remind you how it works, because actually I have dealt with it before. Let me show you how you can go from an ether, and the ether that I'll use is a simpler one. I'll just use a methyl ether. If you treat that with HBr, the first thing that will happen will be that you will protonate the ether on oxygen. That's a reasonable place to protonate it because the oxygen has a lone pair. And whenever you have a molecule with a lone pair and you put it in the presence of a proton, the lone pair is very likely to attack the proton. And now, let me use a different color. This bit that I put in a green dotted circle, that bit is a leaving group. And so bromide ion will come along and do an SN2 displacement. So that is how you can demethylate an ether, by making the ether oxygen plus its attached benzene ring into a good leaving group. Now, when I talked about ethers, I'm pretty sure that I mentioned that if you take a dialkyl ether and you protonate it with HBr and then heat it, the bromide will do exactly the same sort of thing, and you will clean the ether, and you'll get a molecule of bromide and one molecule of alcohol. So that's these reactions now are very, very similar to what you've learned before in the case of aliphatic alcohols. And that's very reasonable because what you learned before for aliphatic alcohols were the chemical properties of the OH group, reactions that the OH group gets involved in. And now I'm still talking about reactions that the OH group gets involved in, except it happens to be an OH group stuck on a benzene ring. So this OH, this oxygen, is not quite as nucleophilic as an oxygen of an alcohol, because the lone pairs are also delocalized into the ring, whereas in an ordinary alcohol, they can't be delocalized anywhere, so they're available in full force. So the rates of reactions will be different, the conditions will be a bit different, but the overall process is exactly the same. Now, what about reactions of the benzene ring itself? Let me clean the board and tell you some reactions of the benzene ring.
I was so lucky when you were totally down.
If you treat phenol with bromine, you can form the tribroman. And the reason for that is that the oxygen is an activating and ortho-para-directing group. And so bromine will go into the para and into the ortho positions, and if you use enough bromine, those three positions will be blocked. If you do the reaction under much milder conditions, You do it at 5 degrees centigrade in a solvent called carbon disulfide, and you use only one equivalent of bromine, you get very largely the para-bromo compound. So this is an example of bromination of a phenol. So all it is really is an example of ortho-para electrophilic aromatic substitution of a benzene ring that has an ortho-para directing group. This happens to be a very, very powerful activating agent, and so it's actually quite difficult to do a monobromination. What about nitration? Well, because the OH group is such a powerful group, you do not need to use concentrated nitric acid. You can use just 20% nitric acid, and if you do that, you will get a mixture of the ortho and the para nitrophenols. So you don't have to use vigorous conditions because the OH group's very strongly activating and it's an ortho-para directing group, and so you get a mixture of ortho and para products. It's quite easy to stop at the stage of the mononitration because the nitro group is a deactivating group. So once the nitro group has gone in, the reactivity of the ring is much lower, and therefore the reaction stops. Now, how can you separate these two? It's a very easy way of separating these. It's rather neat. There's a hydrogen bond between those two. And if you boil that mixture with water, the vapor that comes off contains water and the orthonitro compound, but it doesn't contain any of the paranitro compound, and that's called a steam distillation. When something boils, it means that the vapor pressure above the liquid is equal to the atmospheric pressure. And when you boil this mixture, the vapor that comes off is partially water, mainly water, but some of this, but not that. The reason is that this molecule sticks to other nitrophenol molecules, but this one doesn't. This one just sticks to itself. It's like you've got two hands, one of them's holding like this, but the other one, the other molecule, is holding onto another molecule there and another molecule there. You know, you can imagine some rowdy teenagers having a riot, and the police come along. Some of the teenagers hold hands, but a few of them just stand like this. These are the guys that the police can easily pull out of the mob, whereas the ones that are holding each other's hands are more difficult. It's exactly the same thing with orthonitrophenol and paranitrophenol. What about sulfonation?
Now that I have a watch, I just keep looking at it. It's like, oh, the 2 minutes. What the heck, that my big second? I'm gonna get one after. Yes. That's not for a long time.
Maybe I need to wear a hat when you're
I can, but I kind of feel like it'd be nice to get a haircut. Like I covered it before too, but then they started growing again.
You got them yourself?
Yeah.
I wish I could cut it.
The sulfonation business is a little bit odd. Because what you get depends on the temperature. If you do it at a low temperature, you get ortho substitution. If you do it at a higher temperature, you get para substitution. Now, I mentioned this before. When you do a sulfonation, that reaction is reversible. Now, if you do it at a low temperature, you get what's called the kinetic product. That's simply the product that is formed faster. If you do it at a higher temperature, the initially formed product reverses back to starting materials. The starting materials give you again some of the initially formed product, but also a little bit of the thermodynamically more stable product. And this reversibility keeps going on until everything's drained away to the thermodynamic product. It's not quite true to say everything's drained away, but you get an equilibrium mixture in which the thermodynamic product predominates to a huge extent. So this is just an example of the reversibility of sulfonation. And I mentioned a long time ago that sulfonation is a reversible process. Now there's another reaction that you've not met before. It's called the Kolbe reaction. It's named after Hermann Kolbe, a German chemist. Let me tell you about the Kolbe reaction.
Just what you think about like
Oh, it's probably like a K and like H in the middle or something. He said it was German, did I say?
Oh, is that gonna write? How do you spell it? Just assume it's like seal, or just leave a space maybe. That's fine. I thought it was Cody. Coley? I thought he said Colby.
I heard Colby. I don't know. He said he's German though, that always throws me off.
Just leave a space, put reaction. Just remind yourself to look at it again later. Ready for it?
If you take the sodium salt of a phenol, heat it with carbon dioxide under pressure, what you get is this sodium salt, which on acidification gives you that orthohydroxy acid, which is called salicylic acid. And the way that this presumably happens follow that through, you will see that you get the ortho-salicylic acid. Now this is an approximate mechanism because it doesn't explain why it goes ortho. And probably the reason is that there's a sodium there that binds to those two, so the carbon dioxide is held in such a position that reaction must occur in the ortho position. Now if you take this compound and you treat it with acetic anhydride in the presence of some acetic acid, what you end up with is acetyl salicylic acid. And that thing is better known as aspirin. And so this is an example of the importance of acetylation of the phenolic hydroxyl. Because all that's happened here is that this hydroxyl has been acylated. Now, a few minutes ago, I gave you an example in which I took a simple phenol and said if you treat it with acetic anhydride and a base, or you treat it with acetyl chloride and a base, you'll get the O acetate. And then I pointed out you can treat the phenol with any sort of acyl halide, and you'll introduce an acyl group onto oxygen. Well, here is a simple example of using that to make a commercially important compound that's been used as a medicine for many, 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 many years. Now we come to another reaction, also named after a person. This is the Claisen rearrangement.
Sounds familiar.
Like that's not very nice.
I know how to spell it, so I must have done it.
C-L-A-I. Oh, is there a K?
I thought it was like that. Oh god, maybe it's wrong. Yeah, I think
It sounds so familiar. Crazy. I thought you would be like, Asia.
I need to even not for another month at least. 2 months at
Like,
least.
wow. See, it is a C. You were close. She already knows. Alright, on the next one. Where have I learned this before? Places? It sounds so familiar. So familiar. Maybe. I don't know, everything in the lab's like, it's gone. Do you guys know when our lab marks are going to be posted?
I don't know, my TA said she had marked them already, but she would inform us of our lab marks. I don't know if she's doing that separately or something.
So I thought maybe like...
Yeah, okay.
If you take a phenol and you treat it with a reactive alkyl halide in the presence of a base, what happens is that the oxygen, under the influence of the base, is deprotonated. The O- carries out an SN2 displacement on the reactive halide. In this case, it has to be allyl bromide. And you now get this ether. It's a phenyl allyl ether, or an allyl phenyl ether. So that's exactly the same sort of process that I mentioned a few times before, including today, when I talked about the properties of the OH group. If you convert the OH into O-, the O- can attack an alkyl halide and generate an ether. This happens to be an allyl ether. Now when you heat this allyl ether, somehow the allyl group jumps over there. So what is going on? Let me show you what's going on. You see how I've written it? Now you can count 1, 2, 3, 4, 5, 6. you can see how through a cyclic reorganization of the electrons, you can see how the alkyl group moves. But you'll also notice something else. Supposing I were to label that carbon, initially it starts off attached to the oxygen. But when the allyl group moves, it ends up at the end of the chain. And that you can understand in terms of the mechanism, because by that mechanism, that is exactly what must happen. And that's what people thought when they first speculated about the mechanism. So they did the appropriate experiments. They took some allyl compounds, some allyl ethers, in which that carbon is labeled, or in which that carbon is labeled. They did the experiment and degraded the products and found out that the label is exactly where you'd expect it to be. So we know that it does go through this cyclic transition state by this pathway. So momentarily the aromaticity of this system is lost to give you this, but then it re-aromatizes. Now, there is one other aspect that we need to talk about, and that is the business of what looks like nucleophilic substitution on a benzene ring. You know that if you take methyl iodide and you treat it with a nucleophile, the nucleophile will carry out an SN2 displacement, displace the iodide, and the nucleophile, the nucleophilic atom, will become attached to carbon. If you try
it's just a boot ship because whoever boots me and stuff.
We had like 3 people go by last week.
if you try to do a nucleophilic displacement on a vinyl group, it doesn't work. If you try to do a nucleophilic displacement on a halide, usually it doesn't work. But there are a few cases where if you look at the starting material and you look at the product, you would think that in fact a nucleophilic displacement has worked. So what is going on in those cases where looking just at the product and just at the starting material and at the nucleophile, you would assume that a nucleophilic displacement is happening. Well, it turns out nucleophilic displacement is not happening, even though the product looks like it's come via a nucleophilic displacement. So let me show you how that sort of thing works. Supposing you take that chloro compound and you heat it with hydroxide ion. What you will actually get is that. So superficially it looks like you've done a nucleophilic displacement of the chlorine. But in fact it hasn't happened like that at all, because nucleophilic displacements do not occur on benzene rings. even though the product might look as though it was formed by nucleophilic displacement. So what is really going on? What's really going on is that the hydroxide ion is adding there to give you now this intermediate So you see the mechanism is really an addition of the nucleophile and then an expulsion of the leaving group. It's called an addition-elimination. And that often happens when you have an electron withdrawing group attached to the benzene ring, ortho or para, to something that in aliphatic chemistry is a leaving group. So you've got a chlorine, a bromine, or an iodine on a benzene ring, and ortho or para to it, you've got a nitro group, or an ester group, or a sulfone group, or more than one of these groups. Then the so-called nucleophile can add at the carbon having the chloride or the bromide or the iodide. The aromaticity of the benzene ring is momentarily destroyed, and the electrons move out onto the electron withdrawing group, and then they flow back into the benzene ring, but this time, instead of expelling what was the nucleophile, they expel the other thing. And so now you get this. So although it looks like this has undergone nucleophilic displacement, it hasn't. It's undergone an addition-elimination. Now there's another mechanism by which what looks superficially as a displacement, but isn't, can occur. Now I mentioned it last time, but I'll mention it again. Supposing you heat that with sodium hydroxide at 350 degrees centigrade, what you'll get is that. And you might think that what has happened is that there's been a nucleophilic displacement of chlorine. But it hasn't gone that way. What happens you get something called benzyne. And of course, hydroxide can go in there, and negative charge can be picked up there, and so you get the phenol. So you've got to be careful. You have to bear in mind that SN2 displacements do not occur on benzene rings. There are some circumstances where it looks at first sight as though an SN2 displacement has occurred. But in those cases, the mechanism either involves formation of a benzyme and then capture of the positively charged carbon by the nucleophile, or it involves addition of the nucleophile and then expulsion of the group originally attached to the benzene. Now there's one other way of making benzyne, which I need to tell you about. If you take that amine and of course it will exist like that, because this acid will protonate that base. But if you diazotize this with nitrous acid, you get that, and this decomposes quite easily to give you benzyne. And if you do this in the presence of a diene, then you get a Diels-Alder reaction. Now the only other thing that I want to tell you is that that's the end of the course. What you've seen, ladies and gentlemen, in the last few lectures, that if one takes the very simple chemistry that you had in the previous dozen or so lectures, by combining it in different ways, you can develop quite sophisticated processes and make quite complicated molecules. And some of these reactions that I've done today and in the last few lectures are really just extensions in a different context of reactions that I did earlier. It's a very nice sort of unifying aspect to organic chemistry, although it seems to you perhaps that there are zillions of different reactions. There's a relatively small number of different processes which are applied under slightly different conditions and in slightly different circumstances that lead to the known millions of compounds. Thank you very much. Save that till after the exam.